Good afternoon, everybody, and happy Friday. Welcome to our Pi Day of Giving virtual speaker series event. Today's topic at CSI at Ontario Tech, how bloodstains and biomolecules are giving us new insights into forensic analysis. Now, before we begin today's session, I'd like to start by saying that Ontario Tech University is proud to acknowledge the lands and the people of the Mississaugas of Scugog Island First Nation. Our university campus is situated on the traditional territory of the Mississaugas, a branch of the greater Anishinaabe Nation, which includes Algonquin, Ojibwe, Odawa, and Potawatomi. Today, these lands remain home to many Indigenous nations and peoples from across Turtle Island, and we are thankful to be welcome on these lands in friendship. And because we don't want to forgo this important element of reconciliation, we are also dedicated to increasing our awareness, understanding, and gratitude for the lands that we share. And since we're conducting this series in a virtual space and scattered all across the province, I would like everyone to take a moment to reflect on the traditional territory that you find yourself on today, the treaty that it is covered under, and your own personal relationship with the land. Thank you. My name is Jody Cowan, and I'm the Community Engagement Coordinator here at Ontario Tech. Today, we're wrapping up week number 5 with 10 conversations we're hosting as part of our Pi Day of Giving speaker series. We are so excited to have our Ontario Tech experts here with you to share their research and to help spread the word about our Pi Day of Giving, which is meant to raise funds for students. Now, if you have any questions during today's presentation, please use the Q&A function at the bottom of your screen, and we will do our best to get to them at the end. These sessions are also being recorded and will be posted to our website should you choose to watch it again or share with a friend who couldn't be here with us live today. So do you ever wonder what types of questions forensic chemists and researchers can answer in relation to crime scene investigation? Do TV shows actually stack up? In today's session, we'll examine how bloodstains and biomolecules are giving us new insights into forensic analysis. And I'd like to introduce today's speaker, Dr. Teresa Stotesbury. Hello, Teresa. Dr. Stotesbury is an assistant professor and early career researcher in our Faculty of Science Forensic Science program. Her research program sits at the exciting interface of forensic chemistry, material science, and bloodstain pattern analysis. Her research group characterizes forensic evidence and how they degrade in the environment, and also develop novel biomaterials like forensic blood substitutes for training and research applications. She has published more than 30 manuscripts in the peer-reviewed scientific literature on the topic, and in 2020 was a recipient of the NSERC Discovery Accelerator Supplement for her research in these areas. Dr. Stotesbury regularly collaborates with practicing members of the forensic community and has held a previous appointment of research scientist at the Ontario Provincial Police. Welcome, Teresa, and thank you so much for being here today with us. We're really excited to hear your talk on this exciting subject.
Thanks so much, Jody. I'm going to share my screen now and tell you a little bit about what's going on in my world at Ontario Tech University. So hopefully you can see my slides here. Just let me know if you can't. But hi, everyone. Thank you so much for coming to my Pi Day seminar. My name is Teresa Stotesbury, as Jody mentioned, and today I'm going to tell you a little bit about my world as a forensic chemist, and specifically how we're trying to develop new and innovative technologies to help crime scene investigators get more information about what happened at a crime. I'm also going to tell you some interesting innovations that we're making. We make a bunch of biomaterials in our lab, and today I'm going to show you about some of the interesting biomaterials we make for forensic applications. Whoops. Okay, so what I wanted to do today was just to give you a little tidbits of new research that's coming from my lab. And so if anything is of interest to you, feel free to put a pin in it and we'll come back to it and talk about it in the Q&A session. What I'm briefly going to talk about is my lab at Ontario Tech, the self-dubbed Forensic Chemistry and Materials Lab, just a quick intro to that. And then we'll look at bloodstain evidence in particular. But the field of bloodstains is kind of near and dear to my heart. I've been in that community for over 10 years now. And I want to talk a little bit about how blood evidence is used in crime scene investigation and where we're going with pushing new and innovative technologies in the field and how we can take concepts in chemistry and analytical chemistry and make it more useful for crime scene investigations. And then we'll take what we've learned and put a new spin on some CSI concepts. And I'll tell you a little bit about the materials that I'm developing. Myself and my very talented lab members are developing in the lab. These primarily are in blood substitutes, but we're also starting to work on different types of tissue stimulants in our lab. So where am I? I am a faculty member in the Faculty of Science in the Forensic Science program. The Forensic Science program is an accredited program at Ontario Tech. I'm obviously going to tout it, but it's an awesome program. Not only do we have a bunch of scientists that teach our students the cutting edge techniques in biology, chemistry, physics, etc., we also have practicing caseworkers in our program. So our students get to hear experiences and anecdotes from real practitioners that have extensive crime scene work. I'm a chemist. I'm an analytical chemist and materials chemist, I guess, by nature. And so my lab at the university is in the UA building, and I run the forensic chemistry and materials lab. I'm pretty new on campus, so if you haven't seen me, well, because of the pandemic too, hopefully you'll see me soon. But my lab was established in August of 2019, and so far we're a small, but we're a very mighty group. We have a visiting scholar currently, 3 grad students, 5 undergrads, 2 USRAs, and fortunately our lab has been supported through the University Works program at Ontario Tech, and I've been able to train 3 laboratory assistants, which has been quite nice. Our central instrument right now is called the TA Discovery HR2 rheometer. What does that mean? Basically, it's just a fancy instrument that can do a lot of soft materials characterization. And so that's a central piece of instrument for our lab. And if I just put, one sec, if I just use my laser pointer here, this is our instrument here. What we do, like Jody mentioned, is we are really interested in understanding biomolecules in forensic evidence. We spend most of our time analyzing blood, but really we can do biomolecular characterization of any real type of biological forensic evidence. We also care about things like non-Newtonian fluid mechanics and biomaterial development. So if this is of interest to you, or if anything so far at this point on the forensic program has caught your eye, I encourage you to check out YouTube and look at our program video called The Cutting Edge, Ontario Tech's Forensic Science Program. You can learn more about myself and also, more importantly, my other colleagues and what exciting research they're doing in their groups. Okay, so why we're here today. We're here to discuss bloodstains, but before we talk about bloodstains, let's actually talk about blood itself. Blood, I like to describe it now as the aqua vitae of life. I'm not sure if there's background noise, but sorry about that. Blood, the aqua vitae of life. Blood is a complex suspension. It's a complex suspension of a lot of components. In terms of cellular elements, blood houses our red blood cells. They're the ones primarily responsible for transporting oxygen and removing carbon dioxide from our system. We have our white blood cells, primarily responsible for managing our immune responses, and platelets, keeping everything good to go, making sure that, if by default anything happens to our circulatory systems, it can protect itself, form clots. In terms of other elements in blood, blood is a suspension in water. More generically, we call kind of the liquid components the plasma. It also contains ions, proteins, nutrients, waste, and other gases. Now, what's interesting from a forensic perspective is we need to know and understand what is going on in blood inside the body so that we can understand and determine a lot of the processes that happen that are different outside of the body. Okay, we also care about, what's interesting about blood is that the properties, the concentrations of each of these components are different, not only between, say, you and me, but they also vary within ourselves at different points of the day. And because we care so much about understanding and capturing variation in the forensic sciences, we have to have an idea of kind of the variation in whole blood in vivo and also ex vivo in forensic scenarios when bloodstains form. From a forensic perspective, we care mostly about obtaining, you can get genetic profiles. Again, this is really useful for source identification of unknowns or unknown people, at crime scenes. And also from a forensic toxicology standpoint, liquid blood can be used to determine if there's any illicit substances, prescription drugs, poisons, etc., in the sample. But as a bloodstain person, we want to know what happens to blood outside the body. Is it the same inside the body or out? What happens? And so this is where my lab spends a lot of time and a lot of focus. We care a lot about looking at blood stains. So blood stains form, you can imagine, this is my link to pi from Pi Day. So when blood exits the body, normally in certain mechanisms, droplets are formed, and droplets are formed, they're spherical in nature. So fast fact myth, if you see the little teardrop shape in emojis or I don't know, depicted in infographics, that's not correct. Blood droplets form as spheres, and they oscillate in space in bloodstain scenarios. They all strike a surface in the most part, and then a bloodstain will deposit. They'll start spreading and a bloodstain will deposit. So what you're looking at here is a bloodstain. This is a passive drip stain. Very beautiful photo from one of my undergraduate students, Lalo Rampete. And so what can we get from this bloodstain currently as a crime scene investigator? The first thing that we can do, if we kind of like house this in the 5 W's, what information can we get? We can use chemical methods to first figure out, is this red stain? Because remember, you're going into a crime scene, you don't necessarily know the known. Is it blood? We can use confirmatory testing methods to also say, is this blood human blood or not? We can swab the blood stain and obtain a genetic profile to identify the blood source. Blood stain pattern analysts use the size, shape, and distribution of stains and groupings of stains in some scenarios where there's a lot of research and development in order to provide an interpretation to how the blood got there. So what happened in the events of bloodshed? You might ask why. Well, I'm a scientist, and so it's not our job really to provide an interpretation as to why or intent. We let the lawyers do that, so psych there. But there's a new kind of growing body of research. Actually, I guess it's been around for the past decade or so on figuring out when, or are there ways that we can put a timestamp to how old that blood stain is, not how old the donor is. You can start getting at that through DNA methylation technologies, but how long has that blood stain been around at a crime scene? Because we want to know if that blood stain is relevant or not in terms of the timeline of events to that crime. And there's been a bunch of research. Actually, there's a really nice review paper by Zadora and Menzik, and they talk a lot, particularly around hemoglobin oxidation and degradation, and how we can tap into analytically those signatures to see how they change over time. A lot of these methods are not yet courtroom ready. And so our room, because we're still working on developing techniques with high accuracy and precision, and can also span a significant timeline so that we can make our techniques applicable to lots of different case scenarios in the forensic sciences. So how do we tap at this idea of figuring out that when putting a timestamp onto a bloodstain's age, or the time since deposition, I'm going to call it TSD from this point forward, of the bloodstain? Well, first, before we do that, let's kind of hypothetically think about, well, what happens to a bloodstain outside the body? And right now you're looking at kind of a side profile. Remember that picture that I showed you, the top-down view, that really nice bloodstain from Lello? If we do it kind of an animated version of the side profile of it, this is what you're looking at. We see chemical and physical changes that happen to the bloodstain at different time points. Physically, we see mechanisms like gelation, desiccation, so pretty much water evaporating from the bloodstain, and then we see fracturing across the surface of the bloodstain. So we see a lot of changes in morphology. If you've ever seen an old bloodstain, you'll see it looks kind of like cracky and flaky. And there's been research in our group is also looking at different physical mechanisms for bloodstain changes over time. Chemically, there's lots of really interesting chemistries that happen to bloodstains as they start aging. Some of the primary and predominant things that we see is that the cells start lysing. They kind of burst, break, and all those components will start undergoing other additional interesting chemistries, including oxidation and degradation. We also see the production of what I have labeled here as a VOC, or a volatile organic compound. And the number and types of these VOCs also have, we're starting to see time dependence in those signatures as well. And just, I guess I kind of spoiled it, but we see biomolecule oxidation. And when I'm talking about biomolecules, we're primarily interested in understanding how heme and also DNA and RNA degrades in a bloodstain. So let's check out some of the cool new things that are going on in our lab. So in terms of physical changes to the bloodstain, we've been monitoring surface morphology changes using optical profilometry. The instrument is held in the materials characterization facility at Ontario Tech, which is also a nice analytical facility at the university. So here's what we do. Imagine we took this bloodstain, maybe not this specific one, but we created something similar, like a tiny, tiny little droplet, something as small as 7 microliters. We put it on a piece of steel, and we use the optical profilometer to measure its height distribution over time. This is an example of what an output looks like from an optical profilometer. It looks kind of cool, right? Obviously, the bloodstain's still red, but what you're looking at in terms of different colors is just different scales for heights, where we see really, really higher heights. I think it's on the order of 120 microns around the rim of the stain, and then slowly getting smaller in height profiles as we approach the center of the bloodstain. What's kind of cool is that Braden Bale, who's doing his undergraduate research thesis in my lab right now, has done a lot of work in our lab at looking at how these cracks and height form, these cracks and pits form, and also how the height profile of the bloodstain changes over time. So in just an area scanned of just 1.5-ish millimeters, and scanning every 5 minutes or so, we can see really phenomenal changes to the surface morphology of the bloodstain. And he's doing a lot of the quantitative work here. This is kind of neat because it helps us understand, again, how the bloodstain changes. Are there any physically protective elements within the bloodstain? Again, thinking about it from a chemistry perspective, why do we care? Maybe again, it kind of helps us understand, are these biomolecules protected or not? Are they exposed to the environment? Are there different microenvironmental conditions within that bloodstain, so that again, we can use this knowledge to understand the chemistry and what's happening in these biomolecules. We find that a lot of these changes occur quite quickly, and then as even a few hours after deposition, we don't really see many changes. So Braden he's a 4th year forensic science student, currently completing his thesis, and hopefully he'll have a paper to publish soon from his very interesting results. My second undergraduate student in the lab was Miriam Fakori. She used GCMS, or gas chromatography mass spectrometry, housed by Dr. Helene LeBlanc, to monitor the VOC productions of blood stains, not whole blood. This was kind of a novel study because we were looking specifically at blood stains that were left to degrade in different environmental conditions. And we found that there were different chemical signatures that came off the bloodstain. And I won't spend too much time talking a lot about the chemistry, but basically we found that different types of molecules were generated and found in the headspace at really earlier time points, and then they kind of dissipated and left. And then we also found these interesting productions of amine type of molecules. These are molecules that we find are linked to heavily to bacterial activity, enzymatic degradation, and particularly degradation of blood proteins. So we found that, again, there's time-dependent signatures that could maybe help us understand put a timestamp to those degrading bloodstains. So we're still working on that. We're actually, one of our next projects with an incoming master's student is to link the VOC production to different biomolecules that we still find on the surface with using a different type of mass spec imaging technique, which is really exciting. We can also look at the electric. We can look kind of like at the electrochemical properties of bloodstains. This has been a really fun and interesting collaboration that my lab has had with the Dr. Brad Easton group at Ontario Tech. You may have heard of him and his electrochemistry lab. And what we're doing and what we've done in this study is we form bloodstains on electrodes. So you're looking at a top-down view of a bloodstain. Again, we allow it to crack and degrade as it would normally in a crime scene environment. And we were able to collect a bunch of electrochemical measurements, and I won't go into all of those details, but we were able to see that there are electrochemical changes and oxidation and reduction changes to the bloodstain over time. What was interesting about this technique is we saw a sharp decrease in, or a sharp statistically significant change in these signatures around 96 hours after deposition. And so we're hoping to build this technology into more of an interesting little diagnostic test for this TSD measurement of bloodstains. Mitchell Thiessen was a master's student on the project. His research is just in the process of being submitted to a journal, so stay tuned for that. This research won a poster at the Electrochemical Society of Canada's conference, and Mitch has had a lot of success with the Canadian Society of Forensic Science. So this has been kind of cutting edge research that has seen a lot of press and interesting results from our group, and it's been a great collaboration. Another thing that we're doing, so I talked a lot about heme and whole blood changes, but remember I mentioned that there's changes in the DNA and RNA in a blood stain. Typically, we see fragmentation. We might see differences in conformational changes in the DNA and RNA. And we're trying to get at developing new methods that can look at tiny, small fragments of DNA and RNA so that we can understand pretty much how we can understand and link those, again, to time-wise signatures for TSD. What I should have mentioned a little bit beforehand is that those hemoglobin changes are quite early in kind of the bloodstain's lifetime. The first week or so, 96 hours-ish of a bloodstain, do we see changes in the heme, but then over long amounts of time, weeks, months, and maybe even years, sometimes in the literature, we can still detect some changes in the DNA and RNA. So using that key instrument, the rheometer, we're trying to see if we can develop new and innovative methods to understand how small fragments of DNA and RNA are changing in a bloodstain over time. This has been considered kind of an interesting subject and a new and novel subject in the area, using rheology to do this. And Colin Elliott is a master's student in my lab who's responsible for this project. He's given a bunch of talks, and this was some of his cool results where we see big changes using our rheometer with small, tiny little DNA fragments also at trace concentrations, which is a novel find in our field. What happened at Ontario Tech at the 4th annual CAIUTech Ontario Tech Chemistry Symposium. So Colin just gave a talk there and has received some interesting feedback on that project. So stay tuned for those results as they develop over time. Now, I talked a little bit about these exciting methods that we're using to age bloodstains, but I just want to bring it back to the real world here. So we're in our lab, we're looking at these pristine bloodstains. We can find time-dependent signatures as they degrade in perfect lab conditions. And you might ask yourself, wow, okay, so how does this translate to the real world? And yes, we're thinking about that. So for all of our methods that we develop, we try to simulate degradation in a bunch of different environmental conditions, because we find that variables like sunlight, humidity and precipitation, and temperature all affect and have variable influences on the rate of degradation over time. Two interesting projects from undergrad thesis projects we're primarily interested in really figuring out how bloodstains form in extreme cold conditions. Makes sense, we're in Canada. And Priya Kundan found that we're seeing really interesting crystallization mechanisms happening in the bloodstains that form even less than a millisecond after deposition on an ice surface. And interesting, if you ever, well, hopefully you never see a crime scene in that temperature or at all, but the bloodstains actually go bright orange. And so we're looking into that mechanism. And she did her thesis in my lab. Lalo Rampede is completing her undergrad thesis in my lab right now, and she's looking at the spectral signatures of these degrading bloodstains in different temperature conditions. So we're also understanding the influence of temperature and environmental conditions on this degradation. Okay, so we use all this information, and I know I'm running out of time, so I'm going to go a little bit quicker here. So sorry about that, but we use all this information about bloodstains. We know there's extreme variability in the properties of bloodstains. And we might ask ourselves, if we're going to repeat these studies or maybe go into training labs, we might not actually be able to use human blood for research and training. Is there anything else that we can use or develop that has known and standardized properties and relevant properties that can be useful in forensic scenarios? Can we use other blood sources? Most definitely, but sometimes there's ethical and biohazard safety considerations that need to be used when conducting this research and training. Can we use semi-synthetics and synthetics? Definitely can. There's been an explosion in the literature on developing blood substitutes and tissue simulants. And it's also important that if using anything other than human blood, well, and even using human blood, that the methodologies are valid and the fluid properties are measured. So let's see what our lab is doing. So our lab makes blood substitutes, and a question that I might come back to is, what makes a good blood substitute? Is it just visual appearance? You know, it looks awesome, right? Like Game of Thrones. Do we just care about that as forensic scientists? No, we care a lot more about the fluid properties. Is it useful for oxygen transport? Blood substitutes in clinical studies for sure care about that. We care a little bit about it. We care about it in a degradation context, but the ones that are just trying to mimic stain formation don't necessarily need to demonstrate a lot of oxygen transport properties. We care a lot about kind of the fluid properties, the viscosity, density, surface tension, wettability, and other surface interactions. So some blood substitutes that you see, or fake blood that you see in TV shows, don't necessarily meet the requirements of forensic crime scene investigators. And a lot of my work prior to coming to Ontario Tech was developing blood substitutes. And so we make blood substitutes that are chemically safe. They're free of biohazardous risks. We validate them for the context of the purpose, whether it's creating passive drip stains or impact patterns, or maybe demonstrating chemical reactivity with some of these presumptive tests. We make sure they're valid. We make sure they're easy to fabricate. And we've actually done some work in pedagogical developments and adding, kind of niche little features to our blood substitute to enhance learning and when we're training complex crime scene courses. So these are just some screenshots of some of the blood substitutes we've made in the past that replicate interface interactions, passive drip stain formation, transfer mechanisms, and also chemical reactivity with luminol. Remember, in like maybe some of the crime scene shows, you've seen people spray like the spray at crime scene, and it like glows bright blue. That's a chemiluminescent reaction with this catalyzed by heme in blood, but also by a similar molecule in our blood substitutes that can be used kind of again in training and research scenarios. The last thing I want to talk about today is the newest material that's being developed in our lab. This is a project by our visiting PhD student, Amanda Orr. And Amanda Orr and myself and Dr. Paul Wilson at Trent University are developing these things called calcium alginate tissue gels. And this is a neat little logo, right? It's pretty cool. And so we're making these tissue gels. We're making blood substitutes and tissue mimetics. What's neat about this is the materials that Amanda is making contain DNA. So we've done a really good job in the past at making blood substitutes that can make blood stains, that can react with chemical enhancers. But right now we're making materials that can also contain DNA. And so to replicate the genetic profiles that you could come across in crime scene investigation. So Mandy's working on that. She's found that making these calcium alginate tissue gels, we can encapsulate DNA. We can actually do more than that. We can actually covalently bind DNA into the network of our materials. We can genotype them using standard forensic protocols. What's cool about our materials too is that we're finding that these materials can behave the way that they would in forensic scenarios. When they're dry, they're desiccated, they've had time to degrade in the environment. And we're also developing methods where we can develop technologies where co-amplification of the DNA is possible. And so this work is quite interesting. And in fact, it's had a lot of recent attention in the media. And I'm happy to report that Mandy was one of the winners recently, I think it was like last week or maybe 2 weeks ago, of the Royal Society of Chemistry's annual Twitter conference. She made an excellent poster pitch. So if you're also interested in learning more about that, I suggest you go to Twitter and check out Mandy Orr's profile, where you can see her 1-minute video on her research. A kind of cool thing from this too is a very popular artist developed a cartoon based on her work. No, we don't put seaweed. Alginate's a seaweed polymer that's extracted from seaweeds. And so this is why there's like a little seaweed in the cartoon. Anyway, that's all I have for now in terms of dropping some little tidbits of cool forensic science that's going on in my lab at the university. I've loved working at Ontario Tech. I absolutely adore being part of the Faculty of Science. There's amazing scientists in the faculty. I wouldn't be here and it wouldn't be possible to talk about all these interesting innovations if it weren't for my lab members. And so at all levels, thank you so much for being a part of my lab. And thank you so much for listening today. I'm happy to take any questions that you have about research in my lab.
Thanks so much, Teresa. This has been fantastic. We do have quite a few questions that come in, and I think like the one that is going to just state the obvious, because when people think about like bloodstains and forensic analysis, they immediately go to CSI at Miami and Bones. Do those shows ever get it right? Or is it just pure fiction? Like, is any of that what you guys would experience in the real world?
Yeah, so for starters, one of the questions that I always get more are like, are you like Dexter? Because I do the bloodstain work. I'm not, but yeah, so there's definitely CSI. I don't actually watch a lot of CSI, to be completely honest with you, but the fallacies really lie in the fact that you can't get a result in an hour. It's unlikely. Like, it takes us a lot of time to develop a DNA profile or get molecular signatures from evidence. So, and also there's an issue, like sometimes these tests aren't 100% certain. So we can't, some of the conclusions that are made on the shows might make an actual forensic scientist pretty uncomfortable, because there's always uncertainty in any of our measurements.
All right. So what does advancement in the field of forensics mean to you? So does that mean it's faster analysis or a greater degree of accuracy, or is it a combination of both?
I think it's definitely a combination of both. We're always trying to develop more accurate and precise methods. You'll see across a lot of fields in forensics, the real push is not only to develop new technologies, but the idea of how low can you go? And so you'll hear, we can get traces of this or trace tiny, tiny little amounts of DNA or of blood or whatever from a crime scene and get something useful from that. So that's kind of, I guess, where the field is going.
Awesome. Now, you mentioned your collaboration with the Easton Lab, which is great. Do you think that there is an opportunity for other cross-faculty collaborations that you'd like to develop to benefit the forensic department and maybe even other university research?
Oh, for sure. So the nice thing about forensic science is that it is naturally an interdisciplinary field. You can see that probably a lot that I talked about has interesting nice ties with biology, nice ties with organic and inorganic chemists, math, like if we want to model these time series estimations with more detail, we can do that. And what's interesting is that there's also a human element to crime scene investigation. What are we thinking about when we're doing our analyses? Or what are we collecting everything? Are we approaching the investigation the correct way? And so I can see, a lot of ties with other faculties too at the university. So yeah, I'm hoping to work with lots of people.
Now, you are obviously incredibly proud of the students in your lab. I really loved all the shout outs that you gave them. As a faculty member who oversees all of these amazing students, what does success look like for you? How do you measure that?
Oh, that's a really good question. So what do I love? Light bulb moments. So I love going into the lab, training students and seeing where they are able to connect the theory with the experimental technique. So that to me is like knowing the light bulb moments are happening is really exciting to watch, but also it's nice to see the growth in the lab. I always tell my lab group, whether they like it or not, to try things outside of your comfort zone, because that's how you grow as a scientist. And so our group is now embarking on new methods of analysis, new tools, and we meet weekly, and we all kind of struggle together and learn coding or different analytical techniques. And I think that's a nice way to show growth and kind of success is in the field of science. I don't know if that's kind of anyway, I'm all over the place with that answer, but yeah, I love my lab and my students. They're great.
That's awesome. Now, here's a bit of a personal question for you. So what was it that made you want to get into this field? Like what was it about forensic chemistry and bloodstain analysis that really spoke to you and was something that you really wanted to dedicate your career and your passion to?
That's a great question too. So thanks. Yeah, so I am one of those scientists that just love science in general. And so the nice thing, like I mentioned about forensics, is that it's highly interdisciplinary. And so one day I'm learning things about analytical and physical chemistry. The next day I'm learning things about how DNA degrades. And maybe I'm learning, my group is kind of doing all different types of techniques with a central theme. So that's one reason why I like forensics, is every day is different. The science is quite broad. So there's lots of opportunities to learn. And yeah, I mean, I also think if I can make a difference, if my group can make a difference in a case, and that has, major implications for people's lives and futures, then that's an added bonus to my research.
That's amazing. Well, thank you so much for sharing your expertise here with today. It's been a really an enlightening session, and we're really grateful to have you as part of the Ontario Tech family.
Thank you so much.
Thank you. As I mentioned at the beginning of this presentation, I want to thank Scotiabank for their generous sponsorship of our Pi Day of Giving speaker series. This is our 5th annual Pi Day of Giving, where we celebrate the infinite possibilities of our students here at Ontario Tech. I hope you'll make a gift in support of our Student Relief Fund to help our students who are experiencing financial need. All donations to this program will be matched dollar for dollar thanks to our matching funds program. Our student relief fund has already provided more than $500,000 to students who are experienced need, and that is in addition to our regular scholarship and bursary program. So thanks so much for everyone joining us on the session today. I hope that you'll join us again next week. We have a lot of really exciting presentations coming up. Some topics include the truth and reconciliation and what Ontario Tech is doing around that subject, upskilling with micro-credentials, and one called Wicked Problems and Other Worries of the World. And I think that one's bound to be pretty exciting on Monday as well. So you can find out more on ontariotech.ca /Pi Day. Before we go say goodbye, I'd like to share a quick video with you from one of our incredible students here at Ontario Tech. Thanks again, everybody. Happy Friday and enjoy your weekend. Take care.
There's a celebration going on at Ontario Tech. For the past 5 years, we've been coming together on March 14th on Pi Day of Giving in support of Ontario Tech students. There are infinite reasons why students choose to study here, why alumni are proud to have graduated from here, why professors continue to teach here, and why staff come to work here every day. With your help, we are reimagining our modern approach to learning through the lens of technology. We are delivering an educational experience that meets students in the world we live in today and prepares us for the world we will create tomorrow. Our state-of-the-art buildings provide students with innovative, flexible learning spaces, including collaborative labs and classrooms with leading-edge technology. In these spaces, students can turn ideas into action and make an immediate impact on our world. When you make a gift on Pi Day, you're helping to create future leaders who will contribute and thrive in today's world. You're making an impact that resonates and touches all of us. When you give, we all receive. So this Pi Day, let's celebrate and count all the ways that we can work together to create a brighter future and deliver infinite possibilities for students like me.